I'm Ryan.
I'm TK.
I'm Rudy.
And I'm Thomas.
And this is Team 9's embedded video.
Our project for our embedded systems class was to use 2 rovers to complete 2 unique tasks. We decided to implement this as a follow the leader scenario. The first rover, the leader rover, was to be given a goal to navigate to. Along the way, if an obstacle was detected, the rover would turn, avoid the obstacle, then correct its path to its original goal. This obstacle avoidance could be completed any number of times before the goal was reached. While navigating, the rover would mark its path using a thick black marker attached to its rear. After the leader had completed its task, the second rover, the follower rover, would use the line drawn by the lead rover to navigate to the same endpoint.
Hi, I'm Ryan. I was in charge of the follower rover for our group. The goal of the follower rover was to follow the line created by our lead rover, drawn with a black marker. The way we did this was with a reflectance sensor array. As you can see, is coming into the shot now. Our little rover can turn and follow a line that is anywhere. The way it does this is through there's a series of reflectance LEDs on this reflectance sensor array. Each of these LEDs is powered on for a brief period of time and then powered back off again, and then red as an input. If the input is red as a 0, this means there's white underneath of it. If it is red as a 1, there's black underneath of it. Using this and a couple of switch statements, we can then determine which way to turn the rover or continue driving forwards. The speeds of the motors are controlled using pulse width modulation, and the direction is controlled using an output pin. With these in combination, that's how we control the follower rover and make it follow a line.
For the lead rover, we had 3 ultrasonic sensors that communicated via I2C to the sensory pick mounted up front. Each of them is screwed into an aluminum sheet that is screwed into a wooden piece that's hot glued to the front. Each ultrasonic sensor can record an object at a minimum of 20 centimeters and up to 35 centimeters that it sends to the brain pick. It uses a reflectance sensor on the bottom to know if it's crossing over one of its own lines that it drew with a marker mounted at the back.
So the brain's pick of the lead rover is in charge of processing data from the sensor pick and the motor's pick, as well as determining the algorithm that is used. It takes in sensory data, reporting things like obstacles encountered or if a line was detected, and then processes to determine how far it needs to go to avoid things like obstacles, and then tells this information to the motors to tell it what ways it needs to turn in order to avoid obstacles or get towards the endpoint. As we can see from the picture here, we have an example where the rover got until obstacle O, at which point it turned to the right in this example and avoid the obstacle. The leg A that we have here is the distance that it should have gone if it didn't encounter the obstacle, with leg B representing the distance that it went in order to avoid the obstacle. Angle C is the angle that it turned to get past this. So by using the law of cosines, we can calculate the distance that we need to go to get back towards the endpoint, and we can use the law of sines to figure out the angle that we need to turn to get back to this. This allows for an efficient path to get back to the end goal and allows for no wasted movement.
So for the motor pick, the main things to look and point out are the magnetometer. The magnetometer was used to mainly guide the rover and make sure it made accurate direction changes. With our rover, it didn't have to be specific angles you chose. Any angle should have been able to be customizable and able for our rover to go through and do it. And so the magnetometer was able to give us the angle variability that we needed for that. And on top of that, I worked with a lot of the other code that was built to help the motors move and allow the rover to get from wherever points it needed to throughout the entire project.
In order to control the rover, we created a graphical user interface. so it would be easier to interface with everything rather than sending the messages by hand, one after the other. For the graphical user interface, there's two different tabs. There's the Control Center tab and the Calibration tab. In the Control Center tab, it's mainly useful for getting real-time data as what the current status of the rovers are and the sensors and what they're sensing. You can see there's the start and stop for the lead rover, as well as the reflectance data that's in real time, as well as the ultrasonic data and the gyroscope reading, which tells you the angle in which the rover is currently facing. For the follower rover, you have a lot of the same with the start and stop messages, as well as real-time reflectance data telling you what the reflectance sensors are sending at that moment. In the calibration tab, you have all the different calibration settings, so you can quickly go through and debug certain things, certain movements, and certain actions, rather than going through the entire process over and over again and trying to figure out where the action or the problem occurred. Since we use a robust acknowledge system, we have the acknowledges for the 4 different picks at the top. In the control box, it's a box created for the control rover, and you can send it the rotation angle and the movement distance that you want to go. And then you can start the action. The control rover will send an acknowledge and then send the message to the muscle pick. And you can also simulate obstacles in front, so the entire stop system and avoidance system can be tested. For the lead rover, there's the sensors getting and setting the different motors. For the motor settings, you can set the ticks for the left and right motors and the offsets. These help adjust the speed in which the motors move, so we can make sure that the motor is moving in a straight line, and that the values that it's reading are accurate to the centimeters that we want them to, so it's able to go the distance that we were trying to do. And you can set and get whatever the current values are. For the magnetometer calibration, you can get the 2 X and Y offsets that are used when trying different locations and different settings, as these values do change depending on where you're located. And you can just automatically manually calibrate the magnetometer, which sends a message that does 500 different measurements and tries to see what the offsets are from being a perfect circle. Also over here, for precise measurements, we have dumping and stopping the dump for sensors, so we can read whichever sensors we want at the moment, rather than having all of the sensors send data at once. And then we can stop the reading for these sensors, allowing us to pinpoint exactly which sensors we're trying to read at the moment in order to debug the problems with those sensors, rather than trying to read through a lot of sensor data. On the right hand here, you have the fine controls for the motor pick. You can do simple actions like turning left, right, around, and different movement actions, or a combination of the two in these boxes, just like the control box above, but it goes straight to the muscle pick. And then you can start and stop those. And then at the bottom here, the last thing is just a couple routines that do messages one after the other to demonstrate a continuous flow from one to the next instruction. Finally, for the follower rover, we have all the same settings, setting up the ticks and offsets so we can ensure that the motors are moving exactly as we want them in a straight line and the distance we're trying to get them. And we can get the sensor and stop the sensor data so it can pinpoint exactly where the problem is, and starting when the reflectance sensors actually begin reading messages and stopping when the reflectance sensors begin reading messages.
Our project had some limitations as well, and things we could improve upon. For the line following rover, one of the things I would have improved was adjusting the way we mounted the reflectance sensor array so that it was more accurate in reading the line it was following. Another thing I would have changed would have been the algorithm I used to follow the lines. Instead of using absolute values and switch statements, I would have used weighted values for each of the different LEDs and combined them to create an average of where the line was located underneath the reflectance sensor.
For the motor pick, I will have changed a few things in terms of the magnetometer calibration. in terms of when calibrating the magnetometer, it was a bit off in some directions more than others. So I've put more checks in order to make sure it was the exact same offset in each direction and to calculate away those offsets. In the UART code, I would also go through and change it so that there was a start byte and stop byte. This would have helped in the communication system, as many times we'd have data shifts because we didn't have an exact start and stop byte. So the server wouldn't know exactly when the start byte had occurred and when to actually consider the message for reading, as well as maybe configuring bytes to indicate our key value pairs such that we can say this byte is meant for this type of data and this byte is meant for another type of data in order to make the data flow a lot easier to understand.
I'd say that the biggest limitation for the brains pick was in its algorithm, it used a set degree amount to rotate and a set distance to go for when it encountered an obstacle. So theoretically, if you had a large enough obstacle, it might not actually go far enough, or if your obstacle was small enough, then it might just go a little too further than necessary. So that was a bit of an issue there. So I guess that's what would probably change, is make it more of a dynamic system using the sensors so it rotate and go just enough distance that it needed to go.
So one of the strongest limitations of the sensor pick was the type of sensors and the frequency at which it sent out the data. If it sent out too much data, then the Wi-Fi network would get overwhelmed and some of the data would get scrambled up, off by a byte or two. So one way that I think that we can improve the sensor pick would be stricter criteria for which data to actually send out, and possibly using different sensors other than ultrasonic sensors to read distances below 20 centimeters.